times 2.257, and we end up with 5.094049 plus 2.0449. Now we're going to add those, which ends up being 7.1388949. Square root of that is equal to 2.6719. Okay. So now let's make sure that we are correct. Okay. So what they're telling us here is that 7.138949 should be the same as c squared. $2.6719. So real quick, you can see 2.6719 times 2.6719 is equal to 7.1390. 7.138949. And I could have carried my, the numbers probably kept carrying on. Most cases we're going to carry it to 3 decimal places, and that's it. So we just proved that this formula works. Okay? So what happens now if we change it up? I'm going to move our formula over here. I'm actually going to put it in the center. C squared is equal to a squared plus b squared. That's the original formula. Okay? See where we're at. I'm probably going to back up a minute. Okay. So the next example, which is example 2 on page 78, gives you C, the hypotenuse, and the adjacent, C and B, and we're going to change the angles as well. Or, sorry, not the angles, but we're going to change the values as well. Okay? Alright, so walk through this. Begin with the original formula. C squared is equal to a squared plus b squared. Well, now we don't have a, but we have b, and in this case b is 1.437, c is 1.812. So how do we alter this to make it how it makes sense? So C is always the longest one, okay? So since we have C as a value, we know that we are not ever going to add it together. Anytime we switch the formula, so now we have a squared is equal to C squared, we subtract the formula. When we have C in this part of the equation, it becomes subtraction, not addition. Okay? So in this case, let's go through it real quick. So we have 1.812 multiplied by 1.812, subtraction of 1.437 multiplied by 1.437, we end up with 3.2283344 subtracted from 2.064969. Especially when we are doing squares, exponents, and angles, try to carry out the decimal places as many places as you can. It helps increase the accuracy and makes a very large difference in between the two. Okay? So then we end up 1.218375. But that's still showing us that it's A2. So here, in order to get A, now we find the square root of this, which ends up being 1.1038. Okay? So let's say we knew the value of A and not B. Then we end up doing the exact same thing. But now, we change the formula from A squared is equal to we're looking for B. C squared minus A squared. Okay? That's all we do. If you notice, the C is the first one we subtract. Remember, because it's the largest one. So when we know this is the formula. We just put in the other one that we know. But we're always subtracting either A or B from C. When we were looking for C, this was our formula. Okay? So these three formulas alone, if you write these formulas down, that will help you tremendously. Okay? Want you to read through the Pythagorean theory portion. We want to talk about SOHCAHTOA. So let me read from the book here, and you can write this down, and I would take notes of it if you don't have the book. Is when performing calculations of right triangles, three trigonometric functions are also often used: sine, cosine, and tangent. Each of these values is a ratio between the lengths of two sides of the right triangle. These ratios can be remembered using the phrase SOHCAHTOA. So, first thing, SOHCAHTOA. Three at a time. Sine is equal to opposite over hypotenuse. Okay. Cosine is adjacent over hypotenuse. Tangent is equal to opposite over adjacent. Okay? So this is the ratio between the lengths of the adjacent side and the hypotenuse. In case of the cosine, sine is the relationship between the opposite and the hypotenuse. And tangent is the relationship between the opposite and the adjacent. Okay? So as we break these down, let's walk through a couple examples real quick, straight out of the book. First things first, as you're going through this, especially for the beginning blueprint course, I will probably be giving you this table. Solution of right angles triangles, side and angles known, the formulas to go along with it. Okay? That's on page 79. So let's walk through a couple examples. There we are. Do example 1 on page 80. Okay. 1.375. Also 1 3/8. Okay. C is 2.75, so 2 3/4. What we're looking for is the sine of A. So opposite A, hypotenuse, .5. Okay? Cosine, you can follow the next examples, are the exact same. All right? Tangent's the same thing. Now let's move. We'll get into the angles and that more during the layout. All right? So real quick, we're going to go back to this kind of really messy drawing. Very quick and simple. Notice how I overlaid it here. I can pull a measurement from here to here. I can figure different values out. I can also measure this distance physically. So if I did not know this one, I could measure this one with a tape measure or ruler and say, here's this value. I want to figure out this height. I need to figure the distance. I can do this section here, here, so forth. Now also, what I did in this was I created some sections that maybe we need to figure out. So we've got, for example, we have one here at 90 degrees as well, okay? 3 of them equally spaced at 120 degrees. So if we notice something right here, where it's 60 degrees here, 60 degrees here, correct? So in all honesty, I could measure, I could align these two parts, which this should be back over here. But I should align these two, and I can come out here and make my point to measure as well. I've now created my right triangle. And in this case, I am parallel to my up and down axis here in the center. Okay? So knowing how to figure out the Pythagorean theory can help you do a tremendous amount of layout in math and figure out where points are. Okay? That is it for section 2, unit 2. Please hit up your instructor. If you have any questions as you're working through this as well, feel free to go through the review questions, and then you'll come and take the test from me. Thank you. Have a good day.